Good afternoon. It's my entire pleasure to present this work. It was supposed to be presented by Marina Menshykova, who appears to be my wife and also co-author, but she could not attend, so I will be presenting instead of her. It's a joint work done together with Heriot-Watt University, and it was supported by several funding bodies along many years. So basically what we are going to discuss, so we all know that materials would contain different cracks. It could be interlaminar or intralaminar cracks, and usually if your crack is located at a distant distance from other objects and the boundary of your material, you can consider this crack as a single crack, and you do a model assuming that. In this presentation, we will consider and present a system of cracks, but just for simplicity of analysis and presentation, I will present results obtained for two cracks located at the interface. But the general theory is basically the following. So the statement, it would be basically the same if you have two cracks around. So what do we have? We have different materials, and we have interface crack with obviously some loading applied to material. It may be any kind of dynamic loading. So again, for consistency, I will present the results obtained for harmonic cyclic loading, but impact loading or other types of dynamic loading are also can be easily considered here. And you would have the following mathematical statement. You may describe the stress-strain state of our system using pretty standard Lamé equations. So you would have displacements and the derivative of those displacements, Laplace operator, and for obvious reasons you would need to have some initial and boundary conditions. As initial condition, usually people suggest that you would have no displacement, no deformation at the initial moment. And for boundary conditions, they are different. So on the bonding interface, you would have conditions too. So the continuity conditions, displacements, and tractions would be continuous. For tractions, minus sign appears because of the direction at that bonding interface. And you would have some kind of traction vectors predefined at the crack surfaces. And at the very far away from the crack, at infinity, you would have standard Sommerfeld conditions. So you would have finite elastic energy for an infinite body. Now, what can you do? You can use Samiliana dynamic identity to link together displacements and tractions. So it would look like that with two integrals with respect to space coordinate and time. And you would have those beautiful integral kernels here, U and W. U would be standard green fundamental displacement tensor, which would in 2D case would have the following form with a special representation for psi and xi. In 3D, you would have different psis and xis, and this coefficient would be 4 instead of 2. And you can get W out of U if you apply the following differential operator. So for some specific reasons, for many problems, it would be easier, and instead of equation 3, one would use equation 7, which may be obtained from 3 if you apply the same differential operator 5 to equation 3. This one also links traction and displacements, but for example, for the case of homogeneous body, usually this one is the best one because you can just subtract two equations. This term would disappear, and you would have traction being equal to displacement jump multiplied by the fundamental solution. That's what standard approach suggests from 70s. This kernel F would be the second derivative of U, so the first derivative of W, and it all can be done. Then people usually do limiting transition to the interface, and you would have equations like that. And they may be rearranged. For the case of harmonic loading, we may represent all components of solution as exponential functions multiplied by the appropriate coefficients. And because of that, it's possible to get rid of integration with respect to time. And finally, one would have the following boundary integral equation systems. It looks scary, I know, but it's possible to solve it. And if one would solve it, then just a reminder how psi and xi functions look like. So, when you solve this system of equations, you would need to, as always with boundary integral equations, there are problems with different integrals, in particular with hypersingular integrals. So these are regulated analytically. And finally, towards the solution. So that's how distributions of normal tractions at the bonding interface looks like in terms of time. As you may expect, solution decreases with increase of the distance from the crack, so it would be no effects of the crack existence far away from the crack. And you may get results, you may calculate certain density factors, but before you do that, there is additional step, which is kind of a signature for our research group. We take the contact interaction of crack faces into account, because for obvious reasons, if you have harmonic loading, you would have tension and compression stages, so the crack faces would be in contact, and this contact would significantly change the solution. In order to do that, we imply the following constraints. So Signorini constraint for the normal components of displacements and forces, and Coulomb friction law for the shear components. And component of solution now are represented as Fourier series. The advantage of this approach is the following. If you want to consider standard harmonic solution, then you can just get rid of those zero terms, and you don't have this summation. So you would have cosine plus sine, that is standard solution. So without any efforts, the model solution disregarding the contact interaction can be obtained. And we use iterative algorithm, so we solve the solution problem initially disregarding the contact, and then we apply contact constraints, and solution step by step is changed in order to satisfy those conditions. That's how the solution looks like, displacement jump and contact forces on the crack. The white surface would be contact forces, and the gray one would displacement jump, so we can see that there is no interpenetration of crack faces, and the contact forces are present only where actual contact is. And that's how the solution looks like for homogeneous material. There's a red curve with black circles is the model solution disregarding the contact interaction. Black circles obtained by Zhang and Gross in 90s, and the red curve is our curve, so we can see that that's kind of validation of our solution. And the blue curve, certain density factors, that's solution taking the contact into account, so we can see a huge difference in magnitudes and frequencies for when maximums are achieved. And that's how it looks for different angles of loading, so the difference between results may achieve 50%. So for interface crack, solution looks quite similar. So that is the first mode. That is the second mode. The same similar situation in terms of differences between maximums and frequencies at which those maximums are achieved. And that's how the iterative process, iterative solution looks like with respect to with respect to number of iterations. So we can clearly see the convergence of the solution to some limit for different iterative coefficients, and that's the velocity of convergence rate comparison for different frequencies, and that is the analysis of convergence with respect to approximation properties. I will skip that part, so you can see that for different qualities of mesh, time approximation, number of Fourier coefficients, basically. There is a convergence over there, so that's quite an obvious for different number of Fourier coefficients. So we start from here, then second Fourier coefficient is this one, third is that one, and so on and so on. So basically, as soon as you have about 10 Fourier coefficients, the solution would not change much. And finally, system of cracks, two cracks, as you may expect. So we have the distance between crack centers being equal to d. And that's how the displacements at the bonding interface look like. So we have cracks here and there, and those are normal displacements. And on the next slide, we would see shear displacements of the bonding interface. For obvious reasons, those displacements increases closer to the crack tips. That's more obvious for shear mode, so we can clearly see that's all displacements rising and rising. And as long as we have those displacements and we have appropriate stresses, if you would calculate the appropriate normal displacement jump and shear displacement jump, from which you can easily calculate stress intensity factors, you would see the clear dependence of the solutions on the distance between crack. So there's a solid black line is the line obtained with the distance equals to 15 crack semi-lenses, and it's basically symmetrical one, so there is no difference between minus and plus tips of our crack. So each crack is not aware of the existence of the other crack, as one would expect. And as long as cracks are closer and closer, solution becomes not symmetrical anymore. You can clearly see that the maximums at the closest tip to the other crack would be much, much higher than at the far tip. Very similar situation is for shear modes, the displacement jump for shear modes, and those obtained for different frequencies of the loading, so for different wave numbers. And finally, that's how solution looks like for both modes of stress intensity factor with respect to the distance between cracks. So this dotted straight line, that is the solution for a single crack. And you can see that basically when the distance between cracks more than 6 semi-lenses, you may consider the crack being isolated, two isolated cracks. But as long as they are closer, the difference is huge. And the closer they are, the stress intensity factors are higher. You may expect, so in simple words, two cracks want to become one long crack as long as they are close together. And that's what you would expect. For shear mode, situation is the same, but just the magnitude of the stress intensity factor is slightly lower. And I would like probably to end with this one. So we have some oscillations of the solution for higher wave frequencies, as one would expect, but as before, there is a convergence of the solution to the case of single crack. I believe I'm nearly managed to stay within the time limit. So thank you for attention, and I would be happy to answer any questions you might have.